In this video, what we're going to do is we're going to apply the model of the magnetic force to a charge that is moving in this way in a uniform magnetic field. So a magnetic field that has the same value and points in the same direction everywhere in space. What that's going to do for us is it's going to help us understand what does the motion of charges look like in magnetic fields, but it also will actually help us understand a little bit more about what magnetic fields can do to charges, because it's actually that they produce a very special kind of trajectory. So in this case, what I have is a situation where I want to apply QV cross B to this particle, right? It's a positively charged particle. It's moving to the left. So, and the magnetic field's into the board. So V cross B points down. With a positive charge, you're going to end up having a force that pushes the particle down. So this particle will experience a magnetic force pointing down. So if we look at the update form of the momentum principle, in a small amount of time, the momentum of that particle is going to be tipped downward, because this guy points to the right, and this guy points down, sorry, to the left. And left plus down is going to give you something that kind of points left and down, right? So in the very next instant, what you're going to have is a situation where the particle is kind of moving down and to the left like this. If we apply that again, what we're going to find is that that force, V cross B, points perpendicular to both, so it points inward like that. And so we're going to get a little bit more down and a little bit more to the left. We can keep playing this game, but what we're going to find is that every time we do this calculation, the force will always be perpendicular to the velocity. And this is actually something that you've seen before in mechanics. If you think about an object moving in a circular orbit, as it moves around, the net force that acts on that particle always points inward towards the circle. It's always the same size, and it always points perpendicular to the velocity vector. So this is a case of that we can model with uniform circular motion. That is, if you have a charged particle that has some velocity, and it's in a uniform magnetic field, it will move in a circle as long as it doesn't leave sort of the region where the magnetic field is. Then all bets are off. This idea actually leads us to be able to model the net force in terms of the centripetal force, right? It's not the real force, but it's a model for how the net force works. And as a reminder of that, right, that magnitude of that net force in the sort of centripetal case, that is where the force is perpendicular to the velocity everywhere, looks like mv squared over r, where r is the radius of this orbit, right? So in fact, you can think about it this way. Charges that are moving in uniform magnetic fields actually orbit nothing physical. They just make circles around. But that orbit is caused by the magnetic force, which is pushing on them in this sort of perpendicular fashion all the way throughout. Okay? Now that's really interesting, because what we learned earlier in mechanics was that forces can do two kinds of things to particles. Forces can either speed up or slow down particles, or they can turn them. They can do both, but they can do either of those things. And in this case, with the magnetic field, because that magnetic force is always perpendicular, it turns out that the magnetic field can only act on a particle to turn it. That is, the magnetic force can only cause a particle's trajectory to change. It can't actually speed it up and slow it down. That's really interesting, because that means that magnetic forces can't change the kinetic energy of a particle. It can't actually cause it to move any faster or any slower. So let's see how that works. So if we think about the work that would be done by that force, that would be the integral from some initial to some final location of the force dotted into a displacement. Well, this displacement always points in the direction of the velocity, right? It is just the little step that is in the direction of the velocity. So if we think about the magnetic work that is the work due to the B field, that would be the integral of the magnetic force dotted into the displacement. Well, this guy is always perpendicular to the velocity vector, and this guy is always parallel to the velocity vector. So their dot product is always going to be 0 for every step that we take. So that means that the work done by the magnetic field, or the other side of this energy equation, the kinetic energy that the particle has that can be changed, is 0. So what we've learned from this is that magnetic forces act perpendicular to the velocity vector, and thus they turn particles around. They cannot speed them up or slow them down. And we find that, therefore, we cannot have a kinetic energy change associated with a particle moving in a magnetic field.